Hi everyone, it's Kyle, and today we're going to be going over the last of the Chapter 4 lectures, which is going to be Activity Series and more. Go ahead and pull out your periodic table, because we're going to be referencing a lot of elements and those ions today. Make sure to also pull out your your help sheet at https:/bit.ly/lehelpsheets, case sensitive, and open number 4 to our single replacement redox. This lesson is called Activity Series because we're going to be talking about how active or how likely a element is to oxidize or reduce. So remember before we start that we have our glasses on the side because chemistry is more than just numbers, it's a lens to approach life. Let's jump into it. We're going to write out the first one. Calcium metal is added to a dilute solution of hydrochloric acid. I'd recommend that you pause the video first, write out the reactants, and then write out the products. Cool, so let's write out the reactants. Calcium, solid, that's our metal, plus a dilute solution of hydrochloric acid. Hydro always means that there's an H, and if you have a hydrochloric acid, it's going to be 1Cl because you added the word hydro in front. We'll get into the nomenclatures or how to name these later, maybe in the acid-base chapter, but for now, let's have these as our reactants. And if you haven't predicted the products already, go ahead and pause the video and do that. But if not, let's jump into the products. The products are going to be, well, it's a single replacement. You can see that it also says single redox at the top over here. And so Ca is going to replace H, and H is just going to be left as an ion on the side. So let me go ahead and erase that. So here's what's going to happen. CaCl. Remember we have Cl minus and Ca2 plus, so this is going to be Cl2. We have our solubility rules. Cl as a halide. Halides are always soluble except for Ag+, Hg+, and Pb2+. Aqueous. The last thing we're going to do is we're going to have our H. Now remember that H is always diatomic, so it's going to be H2, and this is going to be a gas. Again, this is kind of something that you would memorize in our nomenclatures as well. We might get into that later in the season. In the lectures later. So now, let's go ahead and let's do our oxidation numbers. So go ahead, stop the video, and oxidize. Balance. 0 for our calcium, because it's just a single element. -1 plus 1. -1 plus 2. 0. So now, we're going to do our standard redox, oil rig. So we care about what in this case is being what's actually being oxidized. So oxidize. Ca is replacing H. Ca and H. Let's think about this for a second. Ca is 2 plus. Ca is 2 plus. It's going from 0 to 2 plus. This, in this case, is going to be our oxidation. It's losing electrons. It's becoming more positive. The question in this situation is going to be, will this happen in nature? And the way we can solve this is by looking at our activity series over here. Will Ca replace H to form CaCl2 and H2 gas? Well, given our activation series over here, we've identified that 1, this is oxidation, and 2, which one has a stronger or more ease of oxidation. In this case, we can say Ca is above H, which is at the bottom. And so in this case, we know that Ca2 plus is going to reduce H plus because it has a greater ease of oxidation as shown by the table. So for this answer, we would write this reaction will occur because Ca2 plus has a increased or greater ease of oxidation than H plus. From there, their answer will be ease of oxidation, Ca, it replaces H+. Let's do another example, except this time, let's think of not Ca plus HCl. Let's think of another one. Hg. Hg, by the way, is mercury, and mercury is just a liquid at room temperature, so I'm going to put HgL plus HCl, aqueous. Don't even worry about writing out the rest of this yet. What we care about is whether or not this will occur. So one, let's identify. Hg replacing H. Hg is giving its electrons to Cl minus. Cl minus is greedy. It wants to be more negative. It wants those electrons. So Hg is going to be oxidizing, so we know this is an oxidation. Two, whether this will occur or not. Let's look at our table. Hg2 plus is below H plus. So this reaction will or will not occur. Go ahead and write your answer using this format above. If you said this reaction will not occur, you're correct, because Hg2 plus has less ease of oxidation than H plus. Great. Let's go on to the next part then. Draw a line through it. The next reaction we have is liquid bromine. So this is number 2 on the help sheet. BrL plus potassium iodide, which is Ki, aqueous. And now we have our Br plus Ki. And again, we could do our reactants and products again, but for the sake of just this activity series and for speed, we're not going to do that. We're going to determine what is actually happening. 1. Br, remember, is a halide, Br minus, and Ki is also a minus. So what's actually happening? We're trying to figure out whether this is going to form Kbr plus I minus. Now, let's think about this. Br minus wants to become more negative. It wants to gain those electrons. Then, that's going to be oxidation. So, it's going to be reduction. It's gaining those electrons. Now, if this is going to be reduction, we have to look at a reduction potential, or how easily is Br or I reduced. I googled this earlier, and this is an incomplete table. It doesn't have Br minus on it, but I'm going to write out real quick Cl, Br, and I on the left. And the ease of oxidation, ease of reduction, increasing ease of reduction is going to be going up. So we can see, does this reaction occur? Well, we're going to look at this again. Br is higher than I. In that case, Br has a greater ease of reduction than iodide. So what we're going to do is we're going to say this reaction will occur because Br minus has a greater ease of reduction than I minus. Same thing. Let's do one more example, except this time it's going to be Cl, same thing, Br, liquid, plus 2 KCl, aqueous. Without writing out the products, will this occur? Fill out steps 1 and 2 and pause the video. If you said 1, this is our reduction, because you can see that these are both minuses, and these Cl minus, Br minus, they want to gain those electrons, they want to be reduced. And then you said this reaction will not equals, can't use that here, not occur because Br minus has a less ease of reduction than Cl. Cl wants to stay there. It has a greater ease of reduction. Now that we have that, we have finished all of our activity series questions. But there's one more part, the end more. So stay with me for a little bit longer, and we're going to do one last question. N2O3 gas plus H2O liquid yields HNO X aqueous? This question is actually given by our hydrolysis reaction, which is right over here. You can see that this is a non-metal oxide, water plus a non-metal oxide over here. And so we're trying to figure out what is this X over here. So let's go ahead and let's do that. First things first, we have to identify what type of reaction is this. Well, this was just mentioned. It's a hydrolysis reaction. Hydrolysis reaction. If this is a hydrolysis, hydro meaning the H or the water, lysis meaning breaking apart. If it's a hydrolysis reaction, is this a redox reaction? Well, the answer is going to be no. A reaction can only be of one type. You can't have an acid-base reaction and a double displacement or precipitate reaction. It can't be the same thing. You can't have hydrolysis and a combination or combustion reaction. Always need to be only one type. This is a hydrolysis reaction, and therefore it's not a redox reaction. Now the follow-up question. If we have a redox, we can have oxidation numbers. But if we have hydrolysis, can we have oxidation numbers? Do each of these atoms have oxidation numbers? Your answer should be, well, yes. Oxidation numbers are always present. Remember that redox means that the oxidation numbers, two of the atoms will have different have different oxidation numbers. One of them will be reduced, gaining electrons. One of them will be oxidized, losing electrons. In a hydrolysis reaction, it's not redox, so these oxidation numbers need to stay the same or the different. They need to stay the same. So let's go ahead, write out all the oxidation numbers, and pause the video. So if you did -2, and then +3, and then you did -2, +1, then you did minus what? +1. So we know that H is always +1. O is going to be -2 because it is always -2. Those are just the rules. Now, what do we have for N? Normally, we would say, oh, look at the charge is going to be something like 0 or something like that. And therefore, we need to find what the X is. Well, in this case, it's a little bit of the opposite, but it's the same consistent logic. Our N over here needs to have the same oxidation number as the N over here because it's a hydrolysis reaction. So I'm going to need to put +3 over here. So what we have is we have +1 +3 minus 2x equals 0. Because this coefficient is multiplied over here. -2 times x. So if we solve this out, 4 minus 2x is going to be equal to 0. You can see that we get the answer is equal to 2. Now, let's make sure that this is right. 2 times -2, that's -4, +3 + 1, that's 4. 4 minus 4 is 0. That checks out. So then, your final reaction will be H2O3, N2O3 gas plus H2O liquid HNO2 aqueous. And so that was using the same thing, our same oxidation numbers, but just in a different way. And so as this is our last lecture, and we may not be able to have the chance to be in class with you guys again, we really hope that you guys have enjoyed the lectures, but more than that, have been able to see chemistry. Again, that's more than just these oxidation numbers. It's more than just the statement about whether something is ease of reduction or ease of oxidation. But you're able to see the glasses on the left. You're able to see chemistry not as numbers, not as equations, but a lens to approach life. We hope that you guys have a great rest of your day. Have a great one. We really enjoy teaching you guys. Thanks so much. Bye.